to share again the screen so we can see the slide. So we looked at the core network architecture and the bare network architecture. So we are now going to focus on the wireless network architecture. Also on the wireless, on the radio access network, we are seeing some evolution of our radio access network. So basically, we have, let's say, 3 RAN implementation. We have our distributed RAN. In the distributed RAN, basically, our BBU, our baseband unit, is on the site together with the radio frequency unit. And we use as a communication protocol, we can use the CPRI or the enhanced CPRI. CPRI is the Common Public Radio Interface, which now with 5G it is enhanced because we have to basically support more throughput based on enhanced mobile broadband application. So we can see also from our radio access network some differences. One difference that we can see is that we have some new radio frequency modules which are called AAU. AAU stands for Active Antenna Unit. In this AAU, we are going to use massive MIMO, so we have a greater number of transmitters and receivers. We can have 32 transmitters and receiver or 64 transmitters and receiver. Moreover, in AAU, the active part is integrated together with the antenna. So inside the AAU, we will also have the amplifiers. And also the AAU has inside some module for some physical processing, like for example, the modulation of our signal. So also the interface to communicate with the baseband unit is different. It is the enhanced CPRI, which supports up to 25 gigabit per second of rate. So with distributed RAN, here the D stands for distributed. Our baseband unit and RF module are on the same place, are on the site. Then we evolved to the centralized RAN. Here the C stands for centralized. In our centralized RAN, we can have our baseband unit at the aggregation layer, so not directly on the site. We will have, for example, a pool of BBU, which are, for example, in one central office, and these are connected to our RF unit that we can find on site. So in this case, the advantage is that we have a flexible resource management, meaning that if we need, for example, more resources, more baseband resources, we can use different BBUs that are on our aggregation layer. The protocol for the communication between our RF unit and our baseband unit is still the CPRI or the enhanced CPRI. The disadvantage, let's say, in here is that we increase the distance between our baseband unit and RF unit. And increasing the distance, we also increase the latency. So if we have some applications which are latency sensitive, this option, this implementation is not so suitable. So we are evolving to the Cloud RAN. In Cloud RAN, we can see that the function of the baseband unit, the function of our G0B actually are split into 2 entities. One entity is called CU. CU stands for Centralized Unit. Centralized Unit. And another entity is the distributed unit. So in here, we can see that we split the function of our baseband unit into centralized unit and distributed unit. The centralized unit is cloudified. So we can find our centralized unit cloudified, while the distributed unit is still physical and deployed or at the aggregation layer as a pool of BBU or directly on the site. So in here, we have also to accomplish a real-time and non-real-time separation, because the centralized unit, it is in charge for the processing for the non-real-time processing, so processing at the higher level of our protocol stack. And we are talking about, for example, the PDCP layer. While the distributed layer, the distributed unit is in charge for the processing of real-time layers, so physical processing at physical layer and MAC layer. So from here, we still have the advantages of having a flexible resource management, but we can overcome the problem of the latency. Because if we have real-time application, we can deploy the distributed unit at the site layer, reducing in this way the latency. But for some applications that have no requirement in terms of latency, like for example, application of Internet of Things, like massive machine type communication, we can have the centralized unit, which is cloudified, directly connected to our radio frequency unit. So this is a very flexible structure. It is called Cloud Run. The baseband unit function are split into centralized unit and distributed unit. The centralized unit, it is cloudified, and it can be far from our radio frequency unit, and then our distributed unit will perform real-time processing. They will be distributed on the site, or we can find them as a pool of resources at the aggregation layer. So we can put together advantages of the distributed run and advantages of the centralized run. So this is the evolution that we are seeing in our radio access network. So how can we deploy our centralized unit? We can have our centralized unit at the central equipment room, or we can have our centralized unit at the edge or local DC. So if we have our centralized unit at the local DC, we have higher control processing and resource sharing. The disadvantage is the higher latency. So it is not suitable for delay sensitive services. While if we have in the equipment room, we are closer to the user, so we can shorten the latency, but the resource cannot be shared in large scale. So we can basically, the centralized unit is connected to less distributed units, so we can command lower devices, a lower number of devices. So this is what changes in the wireless architecture. So we have these differences. Traditional site, we used to see our distributed run, because in our traditional site, we have our baseband unit together with radio frequency unit. They are at the same place. The next evolution is to use the centralized run, in which we have a pool of BBU that are centralized at the aggregation layer. So in here, we can basically manage more sites. We can manage more resources, but the problem is the latency. With Cloud Run, with the separation between real-time and non-real-time, we have the centralized unit, which is cloudified, and then the centralized unit can communicate with distributed unit, which can be on-site or at the aggregation layer again. And so we actually have a new interface. The communication interface between the centralized unit and the distributed unit is called F1 interface. So whenever you see F1 interface, this is the interface between the centralized unit and the distributed unit. Together, distributed unit and centralized unit perform exactly the same function of the baseband processing, the baseband unit. So we talked about the new architecture of our 5G network, but what about the new air interface? In the air interface, in the 5G air interface, we have some announcement with respect to the 4G air interface, and also we have some new technology that has been introduced. So this is an overview of the new air interface technology. So we are going to see that we have larger bandwidth with respect to 4G, and we also have the massive MIMO, which we already mentioned while talking about the active antenna unit. We are going to better understand what is massive MIMO. We have a flexible frame structure, and we still use the OFDM, but we use the filtered OFDM to enhance the spectral efficiency. And about the coding scheme, we are going to use some new coding scheme that was not used for LTE or for the Brazilian technology. And also we have the concept of uplink and downlink decoupling. So we are going to describe all of these technologies, and we are going to see why they are useful to increase the user experience, to increase the bandwidth, to reduce the latency, and to increase actually the spectral efficiency. Also, we have, it is not written here, but also we have higher holder modulation that still can increase the spectral efficiency. So we are going to see all of this technology that we have in our air interface. But before to start with this technology, we are going to describe the spectrum, the 5G spectrum, which are the frequencies that are used for our 5G communication. So actually, we use for 5G two frequency range, the frequency range 1 and the frequency range 2. The frequency range 1 is the sub-6 gigahertz spectrum, which it is divided still into two sub-band, the sub-3 gigahertz and the C-band. The C-band, it is in between 3 gigahertz and 6 gigahertz. So this is FR1, frequency range 1. Then we also use frequency range number 2, which is the millimeter wave from 6 gigahertz to more than 19 gigahertz. This spectrum is also called millimeter wave because the wavelength of our signal is in the order of a millimeter. So let us see which are advantages and disadvantages of these three bands, basically. So at the sub-3 gigahertz, we have the advantage that we have an extended coverage, because you know, the lower the frequency, the larger the coverage. The problem in here is that most of the technology, of the radio technology that we know till now, work inside this band. So we don't have at the sub-3 gigahertz a large portion of spectrum that we can use for our 5G applications. While at the millimeter wave, since we have a very short wavelength for our signal, we suffer from path loss and from penetration loss. But the advantage in here is that it is almost free spectrum. So we have a wide portion of spectrum available to be used for 5G applications. In this moment, the most used band is the C band. In the C band, we have basically up to 200 megahertz of bandwidth, contiguous bandwidth, to be used for our 5G applications. And the coverage is a bit reduced, especially in uplink. That's why we are going to see we use the uplink and downlink decoupling. But in this moment, the C band, this band, is the most used band for our 5G application. So from here, we can see the difference in bandwidth between LTE and 5G. With LTE, we have a bandwidth of 3, 5, 10, 15, at maximum 20 megahertz. While in 5G, with FR1, if we are using frequencies, basically the sub 6 gigahertz band, we can have 5, 10, 15, 20, but also 25, 40, 50, 60, 80, and 100 megahertz of spectrum of bandwidth to use for our 5G application. So the cell bandwidth can be 100 megahertz in FR1, and the bandwidth below the 20 megahertz are defined just to meet the requirement of the existing spectrum. While for FR2, so at the millimeter wave, we can have up to 400 megahertz of cell bandwidth. So we can see that we have very larger bandwidth with respect to the preceding technologies. And here, there is a description of the problem of coverage that we have at the C-band. We said at the C-band, we have large portion of spectrum to be used for our 5G application, but we have an imbalance between uplink and downlink coverage. So we can see from here, this is the downlink, So this is the downlink coverage and this is the uplink coverage. So, and we can see that the downlink coverage is always greater with respect to the uplink coverage. So we have an imbalance between these two coverage. As you know, in C-band, we are using some frequencies, let's say higher frequency. We are going to use the most used frequency is the center frequency at 3.5 gigahertz, for example. So what happens while we're using 3.5 gigahertz? I will explain by using this image. So let us suppose we are transmitting and receiving our signal at 3.5 gigahertz. What happens is that if our user equipment is close to our base station, we have no problem, nor in uplink or in downlink. We can transmit or receive signals at 3.5 gigahertz. The problem is that as the user equipment move far from the base station, what's the problem? The power of our base station is much greater with respect to the power of our terminals. So as our user equipment move far from the base station, our user equipment can still receive a good quality signal at 3.5 gigahertz. But in uplink, if our user equipment sends a signal at 3.5 gigahertz and it is far from the base station, we can see that the quality degrades, has a degradation, too much degradation, so the signal cannot reach the base station. So to overcome this problem, we can use the uplink and downlink decoupling. What does it mean? This means that as our terminal is far from the base station, it can receive the signal at 3.5 gigahertz, so we are still using 3.5 gigahertz for downlink, but for the uplink, our terminal will decrease the frequency. So we will use another frequency belonging to the sub 3 gigahertz spectrum. So for example, we can use 1.8 gigahertz for the uplink, so that we can overcome the problem of unbalance between uplink and downlink coverage. We will find this frequency, this low frequency dedicated to uplink and downlink decoupling as a supplementary uplink. SUL stands for supplementary uplink. So in our spectrum, we will have our supplementary uplink frequencies, which are the frequencies that are used to perform uplink and downlink decoupling. Uplink and downlink decoupling is a technology that is used to overcome the problem of unbalanced coverage between uplink and downlink when we are working at the C-band and the user equipment moves far from the base station. Because in this case, we have a coverage gap of 13.7 dB. This is from some tests that have been performed. So we explained the first new concept that we find in our 5G radio network. So I remind you that actually most of the frequencies used for our 5G, so frequencies at C-band and at the millimeter wave band, they work in TDD, in time division duplexing. They work in TDD because basically since we have problem in the availability of our spectrum, we want to use the same frequency for both uplink and downlink to save frequency resources. So most, not all, but most of the frequencies for 5G work on with TDD technology. And to avoid the problem of coverage in uplink and downlink at the C-band, we use the uplink and downlink decoupling. So we will have some dedicated frequencies, like, for example, this is just an example, 1.8 gigahertz, that are used as a supplementary uplink frequencies to accomplish uplink and downlink decoupling. And here we can see the disadvantages, the challenges that we have at the millimeter wave. So in here we have basically two charts. One is showing us the path loss, and the other one is showing us the penetration loss. For the path loss, we can see from here the difference when we work at 3.5 gigahertz and when we work at 28 gigahertz. So if we consider the line of sight at 100 meters of distance at 3.5 gigahertz, we have a path loss of 103 dB. But at 28 gigahertz, this path loss is 121 dB. As the distance increases, also the gap of the path loss between lower and higher frequencies increases. So we can see from here that at 300 meters, the path loss at 3.5 gigahertz is 121 dB, while the path loss at 28 gigahertz is 139 dB. And again, as the distance increases, also the gap in the path loss increases. So at 500 meters of distance, the path loss at 3.5 gigahertz is 130 dB. And the path loss at 28 gigahertz is 148 dB. This is for the path loss. And Also for the penetration loss, we can see with standard glass or coated glass that, for example, 3.5 gigahertz, we have a penetration loss of 13 dB, while at 28 gigahertz, we have a penetration loss of 18 dB. And with coated glass, the penetration loss at millimeter wave is 38 dB. So actually, at the millimeter wave band, since we have path loss and penetration loss, these frequencies cannot be used to provide a wide coverage. So basically, these frequencies are used to provide better capacity, to increase the capacity of our system. And they can also be used as a backbone. So these frequencies are not used to increase the coverage, because it's not possible. We have problem in path loss and we have problem in penetration loss. So what we can do, we can use these frequencies to increase the capacity of our system, not to increase the coverage. Also, we mentioned previously that we introduce a high order modulation. So we can set the modulation. The modulation is used to represent our signal in a digital way. So basically, we have some symbols belonging to a constellation, which represent, each symbol represents a specific combination of amplitude and phase of our signal. So the more symbol we have, the better we can represent our signal. So with LTE, we used up to 64 QAM in Uplink and up to 256 QAM in Downlink. In 5G, we support in Uplink also 206 and 56 QAM to improve the spectral efficiency. But we have to consider also the distance, again, of our terminal to the base station. Because we know we have 256 symbols representing our signal. But considering the bandwidth, these symbols, the more symbols we have, the more closer will be the symbols to each other, as is represented in this image. So what happens is that if the user equipment is closer to the base station, we can have a very good quality of our signal, so we can use 260 and 56 QAM. But as the user equipment moves far from the base station, some noise is introduced, some distortion is introduced. So what happens is that if we use 256 QAM, these symbols will overlap each other. And it will be not possible to actually demodulate our signal. So as the noise increases, we have to reduce the order of our modulation. So we can use 256 QAM as if we are closer to the base station, and then if some noise is introduced, we can reduce our modulation to 64 QAM, 16 QAM, or also QPSK. So we can use 2 bits per symbol. We can use 4 bits per symbol, or we can use 6 bits per symbol or 8 bits per symbol. So we have also to consider the noise. So we have an adaptive modulation based on the noise which is introduced. If the quality of our signal is very high, then we can use 256 QAM. As the quality starts to degrade, we can lower the order of our modulation up to a QPSK. And another technology that we can see with 5G is the massive MIMO. Till now, we're used to talk about MIMO, multiple input, multiple output. With MIMO, we usually have 2TX, 2RX, or 4TX, 4RX, at maximum 8TX, 8RX. With massive MIMO, we actually can have more than 8TX, RX. And in particular, actually, the most used solution is having 32TX and 32RX and 64TX and 64RX. So by having more transmitters and more receiver, we can still enhance the user experience, because by having more than one, let us suppose we have more than one transmitter. Just to make the example, we can improve, for example, the throughput. Why we can improve the throughput? Because we have more transmitters available to send our data. So we can split our data, for example, in different parts, and each transmitters can send one portion of data. And this data will be transmitted in parallel. So we can increase the throughput. We can increase the data rate. Also, we can increase the reliability. So let us suppose to have, instead, just to understand the concept behind, instead of having just one transmitter, we have two transmitters. What happens? We can send the same data on two transmitters, so that at the receiving side, we can combine the two information to have the correct information. So we increase the reliability. Also, what happens is that while using massive MIMO, we have a great number of antenna elements. So for Huawei, for example, in the active antenna unit of Huawei, we will find 192 antenna elements. With 192 antenna elements, what happens is that the more elements we have, the narrower is the beam, is the transmitted beam. And this increases the directivity. And together with the directivity, this means that we increase the gain of our antenna. And increasing the directivity, we also increase the coverage of our antenna. So with the massive MIMO solution, we can increase the throughput, we can increase the reliability, we can increase the coverage. And another advantage is that having many elements, we can give polarization to our antenna, and we can accomplish beam forming. What is beam forming? Basically, basing on the difference in phases about the feeding that we give to our antenna, we can weight our beams toward to the user equipment. So as is shown in this slide. So actually what happens if we don't use the massive MIMO, basically we cannot weight our antenna. So we cannot direct the beam of our antenna toward to the user. But with beam forming, we can weight our signal and we can direct the beam toward our user equipment by improving the user experience. So this is the gain of the massive MIMO. We can recap what we said. Actually, with array gain, we increase the number of antenna elements to increase the directivity, and increasing the directivity, also the gain is increased. Then we can accomplish beam forming. So, and the beamforming can be accomplished horizontally and vertically. So we improve the coverage and we increase the number of users that we can serve. For example, for Huawei, by using 64T, 64R, we can provide 16 data streams for the user plane. They are data streams, so for the user plane. So that means that we can serve 16 users. And each user, as you can see from here, has its own beam. So the user experience is increased. So we have the multiplexing gain. 16 data streams are supported, and we can increase the system throughput. And also the diversity gain. When we talk about reliability, by increasing the number of antenna, we can improve the transmission reliability because we can send the same data on multiple transmitters, and at the receiving side, we can combine our signals to obtain the correct information, so we are reliable. So here we have the concept of massive MIMO. How we can use massive MIMO in our traffic channel and in our broadcast channel. For traffic channel, we have high gain narrow beam. So we said we have narrower beam that is given by the higher number of antenna element, and we can dynamic adjust the direction of our beam. We can direct our beam toward our user equipment. Also for broadcast channel, we can use narrow beams, and basically to send broadcast information, we can perform a scanning of the environment. So we have different beams that in different instant of time can send the broadcast information. The user equipment can receive more than one beam, but it will select the beam which is the best received beam. So each beam is identified with a particular ID. Then the base station can send the broadcast information, and the user equipment will select the beam which is able for which it receives the best signal. So this is called sweeping, and it lasts 5 milliseconds. So in 5 milliseconds, the sweeping will be performed, and it will be repeated every 20 milliseconds. So every 20 milliseconds, we have 5 milliseconds of sweeping in which our broadcast channel is sent on different beams and different instant of time. So we can increase also we can improve the signal to noise ratio. This is the main concept of massive MIMO. So we have a greater number of antenna elements, we have a greater number of transmitters and receivers, we can improve the throughput, we can improve the reliability, we can perform beamforming, that is, we can direct the beam toward to the user equipment, improving the user experience, and also we can improve the reliability and the coverage, because we are able to to perform beamforming in two directions, in vertical direction and in horizontal direction. And these allow us to increase also the coverage, improve the coverage. So I remind you, this technology, massive MIMO, is used together with AAU. We talked about active antenna unit, AAU. This AAU use massive MIMO. So they have inside, for example, 64 transmitters and 64 receivers, and they also have amplifiers inside. And they also have some processing at the physical layer. So these are the new RF modules which are used for 5G. And as communication interface with the BBU, they support both the, let's say, standard CPRI and also the enhanced CPRI, which allow a rate of 25 gigabit per second, while the CPRI usually allows a rate of 10 gigabit per second. So, talking about the hardware, you will find this new hardware, the AAU. So basically, what happens is that I'm going to share maybe the whiteboard so we can have a better representation. In traditional site, we used to see what we have our BBU, basically our basement unit, which through an optical fiber it is connected to the remote radio unit, and then here we have an RF cable and we have our passive antenna. And here the interface is the CPRI. The evolution is this one. We have our BBU. Our BBU through an optical cable is directly connected to the active antenna unit. The RU is already integrated inside. And in here, we can have the CPRI or the enhanced CPRI. So at the radio access network, this is another evolution that we can see. So I'm going back to the slide again. And to increase the spectral efficiency, we are going to use new coding schemes. So basically, when we are going to select the coding scheme, we have to take in consideration performance, that means the error correction capability and the coding rate. We have to consider the efficiency, so the complexity of our coding and the energy efficiency. And we have to consider the flexibility, so the length of the coder, and also if, for example, HCIA are supported. So with 4G, we were used turbo codes, but turbo codes has good performance, but low efficiency for high speed. So for enhanced mobile broadband services, I remind you that at this moment only release 15 is frozen, and release 15 defines the enhanced mobile broadband scenario. So for enhanced mobile broadband scenario, for the user plane, so for the traffic, we are going to use LDPC coding. So low density parity check coding, which has a low complexity. So it is good for high speed service. While for the control channel, basically, so this is for traffic channels. For control channels, we are going to use polar code that have good performances for small data block. Then, actually, this is defined only for enhanced mobile broadband. The channel coding is not defined yet for massive machine type communication and ultra reliable low latency communication. Please remind that, for example, this is one of the questions that I found in my certification exam. Just to give you an example. One question that I found was about this one, for channel coding. Actually, I think the question was that the question was actually quite misunderstandable, not misunderstandable, but there was a trick, because the question was, in 5G, LDPC are used for traffic channel, while polar code are used for control channel. And one may think the answer is true, but actually the answer is false, because it's said in 5G network. It's not correct. Only for enhanced mobile broadband, we use LDPC for traffic channel and polar code for control channel, not for massive machine type communication or ultra reliable low latency communication. For these two scenarios, the channel coding is yet to define. Okay, so this is just an example. Again, to improve the spectral efficiency, we already talked about F-OFDM. So actually, OFDM technology is still used, but we use the filtered OFDM. So by improving the filtering technology, we can reduce the guard bandwidth requirement so that we can increase the frequency utilization. So, for example, if we make a difference between 5G and 4G, in 4G we used simple OFDM and we needed a 10% of guard band. So 10% of our bandwidth, it was a guard band. But now with F-OFDM, we can reduce the guard band, and we can reduce the guard band up to, for example, 2% of guard band, depending on the system bandwidth and on the sub-carrier spacing. Also, the sub-carrier spacing, actually, this is a new concept again in 5G, because in 4G, we only add one sub-carrier spacing of 15 kilohertz. With 5G, we can have different sub-carrier spacing. So we are going to describe also this one. But for example, by using 30 kilohertz as sub-carrier spacing with a system bandwidth of 100 megahertz, we can increase our spectral efficiency up to 98.28%. That means that we are using less than 2% of guard band. So the spectral efficiency is increased. This by improving the filter technology. So I'm going to describe the sub-carrier spacing in 5G network. So we said I'm going to use again the whiteboard. We said that basically in 4G, our sub-carrier spacing is actually 15 kilohertz. With 5G, we have flexible sub-carrier spacing. In particular, in FR1, we can support a sub-carrier spacing in kilohertz of 15 kilohertz, 30 kilohertz, or 60 kilohertz. And if we consider the TTI, the transmission time interval for when we use 15 kilohertz of sub-carrier spacing is 1 millisecond. With 30 kilohertz of sub-carrier spacing, the transmission time interval is 0.5 milliseconds, while with 60 kilohertz, the transmission time interval is 0.25 milliseconds. In FR2, so at the millimeter wave, we can support 60 kilohertz, again, with a TTI of 0.25 milliseconds, or we can also support 120 kilohertz. So we have a TTI of 0.125 milliseconds. The default sub-carrier spacing in this moment, the sub-carrier spacing that basically all the operators are using in this moment, is the 30 kilohertz. So let's see why it is an advantage to have a flexible sub-carrier spacing. Having a flexible sub-carrier spacing allows us also to have a flexible frame structure. This flexible frame structure is called numerology. So whenever you see numerology, you know that we are referring about the flexible frame structure. And also in here, there is actually an indication about the sub-carrier spacing. So in the numerology, we can define the sub-carrier spacing and also the cyclic prefix length. So I'm going to describe the frame structure by using the whiteboard. So I will change again the screen. So one radio frame lasts 10 milliseconds. So this lasts 10 milliseconds. This is numerology for 5G. Inside one radio frame, we have the subframes. One subframe lasts 1 millisecond. So that means that inside one radio frame, we have 10 subframes. Each of them, it lasts 1 millisecond. Then inside subframes, we have slots. The number of slots changes with respect to the sub-carrier spacing. So if we have, for example, 15 kilohertz of sub-carrier spacing, the TTI is 1 millisecond. That means that inside one subframe, we have one slot, which lasts 1 millisecond. But if we use, for example, I will change color. If we use, for example, 30 kilohertz of sub-carrier spacing, the TTI at 30 kilohertz is 0.5 milliseconds. That means that in one subframe, we will have 2 slots. So slot number 1 and slot number 2. each one lasting 0.5 milliseconds. If we have 60 kilohertz of subcarrier spacing, we will have 4 slots. 1, 2, 3, and slot 4. Each slot lasting 0.25 milliseconds. So we can see from here that within the same subframe, by using different subcarrier spacing, we can send more data. So because, for example, if we use 60 kilohertz, within one subframe, we have 4 slots. So we can send more symbols, more data, because each slot, no matter the subcarrier spacing, but within each slot, we have 14 symbols. So we can see from here that if we use 15 kilohertz of subcarrier spacing, we have 1 slot in one subframe, so we can send 14 symbols per subframe. If we have 30 kilohertz of subcarrier spacing, we have 14 symbols in one slot, so we will have 28 symbols in 1 millisecond in one subframe. And if we use 16, we will have 14 multiplied by 4 symbols inside one subframe that we can transmit in 1 millisecond. So we can reduce the latency. So this is about the numerology. And in here on the slide, you have the reference of the numerology. So in here you can find exactly what I tried to do on the whiteboard. 15 kilohertz, 1 millisecond of TTI. 1 TTI, 1 slot. In 1 slot, we have 14 symbols. Actually, in here we can make another consideration about the cyclic prefix, because actually we have 14 symbols if we use the short cyclic prefix. If we use the long cyclic prefix, then we will have 12 symbols. So here in this slide, we are considering the short cyclic prefix. Then from here, you can see at 30 kilohertz, the TTI is 0.5 milliseconds. So in one subframe, we have 2 slots, each one containing 14 symbols. And with 60 kilohertz, we have TTI of 0.25 milliseconds. So every 25 milliseconds, we have 14 symbols. So in one radio frame, actually, we have, in one subframe, sorry, we have 4 slots. And again, another level of flexibility is the self-contained slot. Again, this helps us in reducing the latency. What is the self-contained slot? We defined the frame structure, the radio frame structure with the sound frame and the slot. Usually these slots are uplink or downlink slots. So for example, let us consider the basic case. We have one radio frame, so 10 milliseconds. In this 10 milliseconds, we have 10 subframe. So this is the frame, subframe. Let us consider, so we have subframe number 1, subframe number 2, and subframe number 10. Let us consider subcarrier spacing at 15 kilohertz. So that means that we have one slot in each subframe. So slot 1, slot 2, and up to slot 10 inside one radio frame. So this slot are slot of uplink or slot of downlink, the entire slot. But now with 5G, we have another layer of flexibility, because inside one slot, we have our 14 symbols. And with self-contained slot, we can dynamically allocate uplink or downlink symbols within the same slot. So what happens, I'm going to share the screen so we can see our presentation. What we have is that we have two spatial slot structure, and these are called self-contained slot. We have actually the downlink self-contained slot and the uplink self-contained slot. In the downlink self-contained slot, the dominant symbols are the downlink symbols. So we have, for example, here we have 14 symbols. Maybe 10 of these symbols are for downlink. 2 of these symbols are for a guard period to allow the conversion from downlink to uplink. And then we have other 2 symbols of uplink. In these 2 symbols of uplink, we can transmit, for example, HARC feedback or acknowledgement or non-acknowledgement information to be faster. So we can still reduce the latency by using the dynamic allocation of symbols. So we can use the downlink symbols to transmit our downlink data, but we can use our uplink symbols to transmit some control information. And for the uplink self-contained time slot, what do we have? We have the opposite situation. The slot is an uplink dominant slot, but we have some symbols for the downlink. And we can use this symbol to transmit the uplink scheduling by saving time. So if maybe in your network or in some documentation, you will see, for example, slot configuration. And you will see, for example, 10.2.2. You know that you have 10 downlink symbols, 2 symbols of guard period, and 2 symbols for uplink. The naming convention is still this one. The first one is the downlink, the last one is the uplink, in the middle we will find the guard period. So, for example, if you find something like this, this means that this is a downlink self-contained time slot. If you have an uplink self-contained time slot, the slot configuration, for example, can be 2.2.10. So 2 symbols for the downlink, 2 symbols for the guard period, and 10 symbols for the uplink. So this is the self-contained slot. Again, more flexibility that allows us to shorten the round-trip time delay for uplink and downlink data transmission. So these are technologies that we can use to reduce the latency on the air interface. So to reduce the latency on the air interface, we use these technologies to reduce the latency. It is to reduce the latency in our network is not enough to reduce the latency only on the air interface. So another key principle is to move the connector closer to the access. And how we can do that, as we said previously, we have the user plane function. We can implement the user plane function closer to the access. So these are the basic technologies that we see in 5G network. So here we have a summary of what we saw today. So today we saw the new architecture. We saw the networking mode. We made the difference between the non-standalone networking and the standalone networking. We said with the non-standalone networking, our 5G network needs the 4G network to provide services. So we have different options. The most used option, family of option in this moment is the option 3. The option 3 series is composed of option 3, option 3A, and option 3X. What is in common between this in this family? That we have the E not B, the G not B, and the 4G core network. And our terminal is in dual connectivity. That means it can communicate at the same time with the 4G network and with the 5G network. Then in option 3, it is the E not B, so the 4G side, the LTE side, which is responsible for the control plane. What changes between 3A, 3, and 3X is the data split point. In the option 3, the traffic is split by the E not B at the LTE side. In option 3A, which is not supported by Huawei, the traffic is split at the core network. In option 3X, the traffic is split at the NR side, at the 5G side. Option 7 is very similar to option 3, but instead of having the 4G connector, we have the 5G connector. And then we also have option 4. In option 4, the control plane is managed by the 5G side, it's managed by NR, by the G not B. And the 4G base station, the E not B, is as a support for the traffic. And then we have the real standalone networking, which is the option 2. In option 2, our 5G network is completely independent. So we have our 5G radio and our new radio. We have our 5G core network, and the network is completely an independent network. Then we saw the features of the core network architecture. We have a control user plane separation. So we saw the architecture, the structure of the 5G core network, and we saw that user plane is completely separate on the user plane, on the control plane. And this allows us to do what? To implement basically the multi-access edge computing. So we can move our user plane function closer to the access network, and this allows us to reduce the latency and also in some cases also to improve the security. So this is for the core network. Then we also saw the differences, the evolution on our radio access network. We said that now on our radio access network, we can find the cloud run solution. With the cloud run solution, we have a separation between real-time processing and services and non-real-time processing and services. So the function of our baseband unit can be split into two functions. So we have the centralized unit, which is cloudified, and the distributed unit. The centralized unit for non-real-time processing and services, and the distributed unit for real-time processing and services. Then on our bearer network, we saw that we can upgrade our layer 2 transport network to a layer 3 transport network. So we basically push the layer 3 closer to the access, and also we can use flexible Ethernet that allow us to perform network slicing at the bearer network. Then on the air interface, we saw how increase the throughput, how increase the rate, and we can do it by using larger bandwidth with respect to the preceding technology. We can use massive MIMO, so multiple number of transmitters and receivers. We use higher order modulation, and we use new coding scheme. So we use LDPC for enhanced mobile broadband services. So these are technologies that allow us to increase the rate. Why? To increase the spectral efficiency, we have filtered OFDM, through which we can reduce the guard band, and we have the flexible frame structure. We can improve the coverage in the C band by using the uplink and downlink decoupling, and in general, we can enhance the coverage by using massive MIMO. And to lower the latency, we have self-contained slot and the control user plane separation. I think this is the centralized unit and distributed unit separation. Yes, it is used also to reduce the latency, but also the control and user plane separation. It is also used to reduce the latencies, but this is not at the air interface. So we saw all of these technologies. So actually we finished the content for today. I remind you again, if you have any question, please write your question on the question and answer window, and then we will collect all of your questions and provide you the answers. Moreover, I kindly recommend you to check this website frequently so that you can have all the upgrade about this project. And also in this website, you will find the answers to your questions, because we will create an FAQ area in here. And also, I hope to see you in the next session of this webinar, and you can access to the webinar also using this web page. So I hope you enjoyed this webinar today, and I hope to see you in the next session. Thank you. Bye.